It's my pleasure to introduce our speaker for today's webinar, Dr. Yuhi Tian. Dr. Tian is an assistant professor in the Department of Chemical and Biomedical Engineering at West Virginia University. Dr. Tian's research focuses on the development and application of systems engineering tools aimed at process innovation, efficient energy solutions, and sustainable process and system integration. Her work is particularly centered on the development of mechanistic and hybrid modeling and analytic tools, optimization algorithms, and multi-scale systems approaches for modular process intensification systems. Dr. Tian received her Ph.D. in chemical engineering from Texas A&M University in 2021, following her bachelor's degree in chemical engineering from Tsinghua University in China in 2016. So with that introduction, I'll turn the time over to Dr. Tian, and welcome.
Hello, everyone. My name is Yuhe Tian. I'm an assistant professor at West Virginia University. It gives me great pleasure to share our work through this CAS webinar series. I would like to thank Professor John Henniger and also the Ph.D. Conference Organization Committee to give me this opportunity. Today, I will talk about the synthesis of sustainable process intensification systems. My presentation will be organized in the following way. I will start with the motivation to address the dual challenge of energy and sustainability. I will then introduce our process design and intensification framework, featuring generalized mass heat representation and also synthesis driven by mathematical optimization and also more recently through reinforcement learning. To start, as we know, the chemical processing industry is the largest energy consumer in the manufacturing sector. It also accounts for a majority of carbon emissions. As per the DOE bandwidth study, if we implement the best available technologies in the current practice, around 19% of energy savings can be achieved. The development and deployment of emerging technologies or even game-changer techniques offers another 30% of energy savings toward the practical minimum of energy consumption. In this way, the innovation of chemical process solutions is really essential to exploit the full potential for energy savings and also to close the technology gap for the energy efficiency towards decarbonization. Toward this direction, process intensification has been regarded as a promising class of technologies toward the non-trade-off solution from all the aspects of economics, safety, and sustainability. The concept of PI can date back to 1980s, starting to develop smaller processes with reduced cost. It has been traditionally regarded as a toolbox with certain technology showcases depending on experimental breakthrough. However, the recent years has witnessed the development of systematic theories on PI fundamentals, such as how to leverage the multifunctional synergy, how to enhance multi-scale joint forces, etc. Intensified technologies has also been playing a key role for decarbonization and electrification. It can either change the way that how we are using energy, such as through microwave heating, electrochemical processes, or lead to the development of novel process units with step change efficiency, such as microreactors, membrane systems, has integrated units, etc. A key question for computational research is how can we systematically generate intensified process designs based on these fundamental principles? And with the resulting modular or intensified unit operations, how can we integrate them with the existing process structure? And on the top, how can we achieve substantially improved metrics, such as these defined by the AICG Rapid Institute, more than 20% improvement on the energy efficiency, double energy productivity, etc. To address some of these challenges, we have been developing a generalized modular representation framework for process synthesis, intensification, and innovation. The framework is built on a novel phenomena-based perspective to capture process systems from a lower aggregated level, and using superstructure optimization and reinforcement learning to systematically generate unit operation and flowsheet designs. In this framework, we also explore a little bit what the lack of mechanistic model, which is very true for many emerging process systems such as microwave heating. So how can we use experimental data to incorporate these techniques to systems level integration and analysis as soon as possible? In the following of this presentation, we'll be zooming into each component one by one, and let's start with the phenomena-based representation. As we know, conventional process synthesis uses unit operations as the elementary building blocks for superstructure representation, and mathematical optimization will identify the optimal selection of these unit operations and also their flowsheet interactions. However, the pre-postulation of which unit operations should be included may sometimes hinder the discovery of non-intuitive or innovative process design solutions. On the other hand, unit operations can be regarded as an aggregation of more fundamental phenomena building blocks, such as reaction, separation, cooling, heating, mixing, splitting, etc. Using these phenomena building blocks to represent the process superstructure may open up the opportunity to identify novel process solutions, including the reinvention of conventional unit operations. Motivated by this, phenomena-based process synthesis has received increasing interest from the community, with some of the pioneering work listed here. Our solution towards phenomena-based synthesis is through the Generalized Modular Representation Framework. GMF utilizes two types of phenomena building blocks: a pure heat exchange module, where the two contacting streams can perform heat exchange, such as heating, cooling, or heat integration, and another mass heat exchange module, where the streams can perform reaction, separation, reactive separation, etc. The representation hierarchy of GMF thus starts from the complex building blocks. From each of the building block, diverse process tasks can be identified, and then the connection of these process tasks can lead to different unit operation or flowsheet designs. So the key question is actually lying here. How can we identify different tasks from the same unified phenomena building block? And what is the key advantage for such compact building block representation? And what are the underlying model formulations to enable this systematic identification? Using mass heat exchange model as an example, our solution is the Gibbs-free energy-based formulation for driving force constraint. Let's use the example of a liquid vapor system, which may be included in distillation system. The starting point of driving force constraint is the decreasing of the total Gibbs-free energy based on the second law of thermodynamics. And to mimic this decreasing trend, and please note that we don't enforce any of the equilibrium, only the decreasing of the Gibbs-free energy. We use two terms to mimic the decreasing trend as a function of the process variables. The first term G1 as a function of the change in molar amount in the inlet and outlet streams, and the second term G2 as the derivative term of the partial total gift-free energy versus the partial molar amount. What is surprising is that the further expansion of this G2 term comprises two parts. The first part, in the form of the separation constant, is dictating the existence and also the extent of the separation task. And the second task is concerning the reaction as a function of the reaction extent. With this observation, we use auxiliary binary or 0-1 variables to denote the existence or not of the separation task, reaction task, or if they both exist, leading to an intensified reactive separation task. The key advantages offered by the driving force constraint is to let mechanism of first principle to determine the synergy or not between these multifunctional phenomena such as separation reaction. And also it contributes to intensify the mass transfer toward the thermodynamic limits. And at the meantime, the representation of the mass heat exchange model remain compact and aggregate for physical representation, and also greatly contributing to keep a tractable computational load. With the representation of each phenomena building block, we then formulate a superstructure representation from which different process alternatives from the structural point of view can be generated. The GMF thesis model is formulated as a mixed-integer nonlinear optimization problem, including the compact physical model, mass-energy balances, phase defining, thermodynamic, kinetic, driving force constraint, etc., to represent the physical phenomena taking place in each of the modules, and then a structural model to generate different design alternatives in an aggregated manner. And on the top, an optimization objective, which can be defined against cost, energy consumption, operability, etc. With the basics of GMF, let's look at how it works to generate different types of intensified systems. We will first look at the combined reaction separation systems, which is a classical application for process identification. Here, we use the olefin metastasis as a representative example to produce butene and hexene from pentene. Here, we integrate the use of GMF also with attainable region theory. We would like not only to identify what is the optimal process design solution, but also how good is the resulting intensified design against these ultimate performance limits set by attainable region. And as we can see here, multiple design alternatives can be generated from GMF and then benchmark with the best possible performance limits set by the attainable region. We have also performed a collaborative case study with Dow Chemical Company for massive mass acrylate purification. In the patent design by Dow Global Technologies, a divided wall column configuration was proposed, which featured around 7.6% more recovery of the MMA compared to the conventional two column in sequence design. And using GMF for grassroots design for this MMA purification example, we start with the GMF superstructure representation with the heat and mass heat exchange modules and identify the optimal GMF design solution. These modular representations will be further validated with unit operation-based design and simulations such as Aspen Plus. And GMF has been successful to identify new precise design solutions featuring the structure of a dividing wall column, decanter, and also a flash column, and featuring around 30% of the utility usage reduction and also around 50% equipment size reduction compared to the state-of-the-art patent design. We have also applied GMF for retrofit design and also for the synthesis of conventional design solutions to benchmark. In addition to distillation-based systems, we have also looked into membrane-assisted reaction systems. The first question here is how can we capture the role of membrane? And the answer to this is particularly benefited from the unified Gibbs-free energy change-based drain force constraint because the feasibility of the mass transfer through the membrane is also governed by the difference of chemical potentials. In this way, using the drain force constraint and the membrane feasibility constraint, we can systematically identify if there's synergy between membrane separation and reaction or not, thus leading to the identification of an intensified membrane-assisted reaction module or a conventional reaction module, again using the mass heat exchange module as the basic phenomena building block. To further capture the distributed process systems such as the membrane reactor systems, we have proposed the GMF with coupling orthogonal collocation of finite elements. A key advantage by GMF OCFE is only introducing the continuous variable to improve the intra-modeling of the GMF mass heat exchange module without further increasing the combinatorial or 0-1 missing interval variables, which would be challenging for the superstructure optimization. Here we have compared GMF OCME representation versus the models in series type of representation mimicking the compartment models, and we have shown the superior modeling performance of the GMF OCFE. We have also invited the micro-reaction systems, which is the very beginning of the intensification technologies. To capture the role of the miniaturization, we ask question what is dictating the choice of a conventional larger-scale reaction versus a micro-reaction system. Here we propose the use of the second Dampoler number, which is dictating the relative importance of the reaction rate versus the diffusive mass transfer. The latter becomes significantly more important when the reactor scale is miniaturized. And the preliminary results have shown that there may exist boundary conditions below which the macro-channel type of miniaturized reactors may overperform and above which the macro-channel reactors may perform less better than the mesoscale or conventional scale reactors. The key here is that how can we make a systematic decision on the choice of scaling up versus scaling down. In the previous presentation, we have been talking about the synthesis and representation capability of different types of modular and or intensified systems. Another note we would like to quickly make here is about the integration of design and operability. A key question for intensified systems is that the integration of multiple tasks may reduce the degree of freedom and may reduce the operating window of the resulting unit operations. So how can we synthesize optimal intensified designs, but also guarantee desired level of operability? In our previous work, we have incorporated flexibility analysis and risk considerations with GMF, which results in an iterative framework to generate optimal GMF designs, but also with desired operability. An illustrative case study on the MTBE production. Here we can see that if we implement cost-driven objective functions, we will identify a single column type of structure with 5 mechanistic change modules. If a further constraint we would like to accommodate uncertainty and to increase around 10% of feasible operating range, and simultaneously we would like to reduce the overall process risk for inherent safety considerations. The optimal design will lead to a reduced number of the modules compared to the cost optimal one. If we push further for safety considerations, we have observed the optimal designs with a sized column type of structure. In other words, the inclusion of more degrees of freedom contribute to the enhancement of the operability. And of course, so the price paid is by the cost objective function. And for the identification with the corresponding unit operations, we can identify the different corresponding design structures. And the key message here is that the incorporation of the operability considerations, even at the phenomenon design stage, may lead to the discovery of different design structures with notable operational or structural changes. For more information, we would like to invite you to look into our framework development for the synthesis of operable process application systems, which can be referred in our published work. In addition to the process synthesis representation, the integration of design operability optimization, so the Synopsys software platform also features a model library with verified dynamic steady state and circuit model to support the different design or operational analysis objectives. In the previous part of the presentation, we have discussed how to leverage phenomena-based representation with superstructure optimization to identify novel intensified design solutions. However, as can be noted, GMF and many general process synthesis problems that may lead to large-scale, highly nonlinear and non-convex optimization problems. So how can the emerging machine learning techniques help us to improve the efficiency of synthesis solution and to intelligently generate process designs? In collaboration with Keylogic and PNL, we have developed an RL-driven process synthesis strategy. More information is included in our Ph.D. conference paper through systems and control transactions. Herein, the goal is starting from a process unit pool, including the maximum available unit operations such as flash, mixer, reactor, heater, cooler, etc., without any superstructure pre-calculation, using the RL algorithm to identify the feasible design solutions and ideally the optimal design solution. I would attribute all the efforts and contributions from my collaborators, and just for a very brief overview on the algorithm. Starting with reading in all the candidate process units, an initial flowsheet can be randomly generated, or any feasible solution that is already known can be set as the input to the first step of the process algorithm. And the flowsheet will be reformulated in the form of the inlet-outlet stream matrix, which will serve as the observation to the algorithm, and some basic connection rule pre-screening, such as the heater cannot be directly connected with cooler, at least one unit operations, etc. And then the flowsheet will be passed to simulation, where we are using the IDAs platform, and the objective function, if any degrees of freedoms included, the objective function value will be used as the reward going to the RL algorithm. The agent is designed using the DeepQ network, and it will determine the action to generate a new design, such as to add a new unit operation, to change the stream connection, etc. And then the resulting new design flowsheet will be going back to the loop until a maximum number of iterations is achieved. And as a very quick example for the HDM process design, here we show the list of the maximum available unit operations. And for the design, the R algorithm can use any type, any number of these unit operations up to the maximum available ones. And different process design alternatives can be generated, and we can benchmark them at the end of the algorithm against different metrics such as productivity, revenue, etc. Some of the challenges we have observed with the RL-driven design is that because of the no population of the superstructure, so we have observed a large combinatorial design space, which makes the RL algorithm very computationally expensive. However, this has also created a natural link with the more compact process representation via GMF, which we are currently developing toward the RL-driven GMF synthesis, where we use the heat and mass heat exchange representations to generate process designs driven by the RL agent. And we are also in collaboration with Cornell University trying to implement quantum RL to expand the design space search. In the very last part of this presentation, we would like to very briefly explore the scenario where the mechanics model is still at the very early stage of development, and how we can incorporate the systems analysis for these emerging technologies just with experimental data. To justify the need toward this, we use the example of microwave-assisted ammonia synthesis. Microreactor presents a promising alternative to the classic copper-bolt process, which is operated at high temperature and high pressure. Due to the advantageous feature of microwave heating, which can selectively heat up the catalyst, the proof of concept experimental studies have shown that microwave-assisted ammonia can be operated at lower pressure and at lower temperature and lower ambient pressure. However, due to the multi-phase from gas and solid multi-scale, the catalyst particle to the reactor box scale, and also the multi-physics, especially the electrical mechanism presented in the microwave reactor, the model development of these systems are still at a very early stage. Our research work has developed a small integrated neural network based on the limited around a number of experimental data. Around 50 data we are using in this were presented in the FOCAPD conference poster, and we apply synthetic minority oversampling technique to generate more synthetic data to bridge the gap between the limited amount of experimental data and the large amount of data needed for the machine learning analysis. And then we use just simple neural network is enough to generate black box data-driven model for this microwave-assisted ammonia process. And here is the comparison between the machine learning predictions versus the experimental data points. We would like to highlight here it is important not to only validate the prediction accuracy for the discrete data points, but also attach importance to the continuous trend prediction, which is very important for the next step optimization prediction. To conclude, in this presentation, we have discussed two types of representation approaches. Just to recap, the generalized model representation to capture chemical processes using mass heat transfer modules, and also how to include the emerging non-process technologies just based on tens of the experimental data. We have also discussed the solution strategies using mathematical programming and also more recent development for reinforcement learning algorithms. The key is to evaluate where the different design alternatives in a unified modeling framework and use the state-of-the-art optimization machine learning strategies to drive the synthesis and the discovery of novel process design solutions. For more information, we would like to invite you to check out our author book together with Professor Piscopoulos at Texas A&M University throughout my doctoral program. Here we have discussed the survey of recent PSE advances in process identification systems, and we have presented the entire process identification synthesis and operability framework with step-by-step guidance and demonstration on the case studies, and also our synopsis software prototype. For the acknowledgement, I would really first like to acknowledge my doctoral program at Texas A&M Chemical Engineering, because this opportunity is really created through my dissertation. I would like to thank my PhD advisor, Professor Piscopoulos, and my committee members, Professor Ahawagi and Professor Hassan, whose guidance and long-lasting support has always been instrumental for my career development. I would also like to acknowledge ASH European Institute for their support on the process intensification synopsis project. I would also like to acknowledge my ongoing funding support and also my research group at West Virginia University. Thank you all for listening to my webinar, and I will be more than happy to take any questions through emails and other communication methods.
Thank you, Dr. Tian, for that excellent presentation. As this is posted on YouTube, please leave comments or questions here on the video, and we'll do our best to direct those to Dr. Tian for her to answer those. Or please reach out to her, as she mentioned, through other means like email or LinkedIn. Thanks for joining today, and I appreciate any comments or questions that you may have for Dr. Tian.